Session. Okay.
Good morning, everyone. We're team number 4, and we designed and built a main aero vehicle with fire extinguishing, grenade release, and inspection system. The team is composed by Ale Colina, Cesar Beltran, and myself, Miriam Freitas. Okay, UAVs are becoming very popular in recent years because they are able to perform tasks without dangerous tasks without putting at risk the lives of any humans. That's why we decided to include the fire extinguishing purpose on this UAV, so first responder personnel wouldn't have to take that much risk when extinguishing a fire in a high-rise building, because they wouldn't be directly exposed to the flames. The objective of this project is to create a fire extinguishing release mechanism that will eject this fire extinguishing ball, which is filled with chemicals that extinguish fires, inside the room of a building that is on fire. It has to be like a really tall building, so it will have the exact purpose for our project. And also we're including a camera that is going to help for guidance and fire inspection. The design and main components of the quadcopter. The design of the release mechanism is based on the specifications of this ball, which has 14.5 centimeters in diameter and weighs 1.5 kilograms. The release mechanism was based on this, and therefore we included that on the frame of the quadcopter, which has 4 motors, 4 propellers, the electronics, and the base of the ramp. The constraint of the project. Our first constraint is stability. When the ball is going to be launched, it's hard for the quadcopter to maintain stability, so we always have to keep that in mind when we're designing the components of the ramp. The way it works is that the springs are pushed back manually with this launching ring, and when they're released we're using the control and the servo motor, the controller will hit a switch, and this will go down and it will release the mechanism, which will push the launching ring plus the ball outside. The specifications for the extinguishing ball already set them, and the agent that is using is non-toxic monoammonium phosphate, and it has an operational effective volume of 9.12 meters cubed. This is how the ball works.
This is the specifications for the frame. We decided that we needed a very light and resistant frame. That's why we chose carbon fiber tubes for the arms and legs. And we have G10 material for the plates, which is holding all the electronics of the quadcopter. That's where these are the electronics of the quadcopter. We have the R2 pilot, that is the brain, which acts as the brain of the quadcopter. That's where all the components are connected. We have a motor that's able to lift 3 kilograms at 44 amps. And the way that we calculated this is that we calculated that the quadcopter is going to weigh between 3 and 4 kilograms. That's without the wrap on the ball. So we needed to be double that in case we needed to change the design of the wrap. So we have a total of 12 kilograms thrust for the quadcopter.
Okay, the main components of the ramp are going to be 2 aluminum tubes, 2 springs at the back, the sliding rim, the hook that is going to release the release mechanism, and the servo motor. The ramp design. We use the principle of work and energy to develop the ramp design. We know that this principle considers the location of the ball and the sliding rim along the path, and analyze the work and the loss and gain of energy during position number 1 and position number 2. Position number 1 is when we compress the sliding rim and the ball is going to be ready to launch. And position number 2 is when the ball and the sliding rim are going to be at the end of the ramp. As you see in the equation of the bottom, the first term is going to be the kinetic energy in position number 1. The force acting on the system are going to be the weight of the ball and the sliding rim. We are going to treat this as just one body. We are going to multiply that for the length of the ram at the angle that we are going to have for the ram. The next term is going to be the force that is going to provide the two springs that are going to be at the back. That is going to be, the next term is going to be the friction force that we are going to have between the sliding rim and the tube. That is going to be equal to the kinetic energy at the end of the run. Using this equation plus the trajectory equation, parabolic equations, we create a spreadsheet where we can change some values. The values that we have fixed is going to be the ball and the sliding rim. We are going to treat these two bodies just as one. The weight is going to be 16.75 newtons. The length of the ramp and the angle, we can change it and we can improve it. We improve it at the in different stages of the design. And the springs, we choose 3 different springs. We are going to have the limitation of the diameter of the tube that we choose. It have to be higher than that if we choose to have just 2 springs at the back. The ram length is going to be a critical design for us. We conclude that the final velocity at the end of the ram for the ball is going to be affected by the length of the ram. As you see in the equation of the bottom, the second term and the third term is going to be affected by the length of the ram. As we increase these 2 values, this part of the equation is going to decrease and the velocity at the end of the ram is going to decrease too. For that reason, we have to find the shortest length ram that we can, but always keeping in mind that we have to have like a safety factor just in case that the ball doesn't travel enough distance in X and it can hit one of the propellers. For that reason, for our design, the best value is 0.25 meters in length. But with that length, we are not sure we have the safety factor of the ball. For that reason, we went beyond of that point. It's going to be 0.35 meters for the length of the ram. Next, we choose 3 different springs. The K for the 3 different, we get some, from the spreadsheet, we get some data for the range of the K that we need. Is going to be, spring number 1 is going to be 656 newtons over meter. Spring number 2 is going to be 856 newtons over meter. And spring number 3 is going to be 1082 newtons over meter. Next. As you see in this graph, as we increase the value of K, we are reaching the highest point. We are reaching highest and highest point. That is going to be for spring number 1, 2, and 3. The ramp angle, we notice after 45 degrees, we are going to start reaching the highest value as we want in Y direction, and with respect at that distance, that's going to be the X direction. Always keeping in mind that the 0, 0 is going to be the tip of the ramp.
Okay. Another main component of the release mechanism is the launching ring. The requirements for this is that it will have to fit the ball plus the rails inside it, so we will push it back to push back the springs too. We base our design on the main plate of this quadcopter, which is this one, because it will fit perfectly to include the release mechanism with the quadcopter without doing that much modifications. After we did this, we realized that we needed holes in order to be able to figure out the configurations of how many springs will we actually be needing and how many rails we will actually be needing. So that's why it has 8 holes. And we needed an optimal sliding performance. That's why we decided to go with aluminum D6061 because it's strong, lightweight, and it has a good performance with the rails. While designing this, we went through 3 stages. In the first stage, we had that the disc thickness was 7 millimeters, the thickness of the bushings were 6 millimeters, and its weight was 1 kilogram, which was too heavy because at the moment of launching the ball, if the spring was going to come to this side, the weight of the quadcopter on this side was going to be too heavy and it was going to lose stability too easily. That's why we decided to go with the second stage, in which we cut holes in the ring, and we went for a weight from 1 kilogram to 0.5 kilograms. We did a static analysis, and we found out that the factor of safety was 12.05, in which we had room for improvement because we wanted to keep reducing the weight. Therefore, we went for the third design, in which we reduced the thicknesses of the ring. We reduced the thickness of the back and the thickness of the bushings. They went from 7 millimeters to 3.8 millimeters for the disc thickness, and for the bushing thickness were from 6 millimeters to 3 millimeters, and it got to a final weight of 0.3 kilograms, which will give us a factor of safety of 1.77, which was satisfactory for our purpose.
For the hook design, we decided to use the same material as for the blade. We use aluminum T6061. We have an L shape, and the position of this, we chose it carefully because we wanted to be totally aligned with the blade, so all the load is transferred onto the frame and not into the servo motor. The location of the servo motor works as it's only working to pull up the blade, and this is the location. So we have all the springs pulling back together, pulling the blade together. We hook this cable right here, and then we can just adjust the location of the servo motor. That way, we found the best place to put the servo and the length. We calculated the length of the hook.
Okay, testing. To prove our designs, we decided to come up with testing stages. The first one was ground testing, in which we're going to prove first the effectiveness of the spring chosen, and second, we're going to prove the performance of the entire release mechanism using the servo motor, the hook, the ring, while activating it using the control. And the third stage was air testing, which was proving the entire performance of the quadcopter by having it flying and also throwing the ball, and we were going to test its stability and how long the ball will travel. For the first part of testing, we used the 3 springs that we set at the beginning. We bought the 3 of them, and we included them only on the ramp, which you can be seen there. It had the base plate at the beginning, and we were just testing for the distance the ball will travel from the tip of the ramp to the ground when it first hit the ground. The result of this testing was that instead of using springs number 3, which were set in theory, we were going to use springs number 2. Why? Because they were more easy to push back by a human, and it provided more, while doing the testing, they provided more distance for the ball to travel, more force. And the second conclusion from this test was that the base plate needed to be replaced. It needed to be removed from the mechanism because it was flexing too much and it was deforming the rails of the ramp.
Okay, the ground testing we performed just for the release mechanism. As you see in the first picture of on the left, we set up a rule in Y direction, and this is coming from one of the videos that we are going to show at the end. The idea that we want to see over here is how much is going to be the height of the ball at the distance that it's going to travel. For this test, the ball height is going to be 0.20 meters, and the distance in X with respect this highest point is going to be 42 meters. After this testing, we did air testing too. This is coming from one of the videos that we are going to show at the end. We set up the same rule in horizontal position to be able to measure the distance that the ball is going to travel. As you see in the second picture, the ball is traveling, it's already outside of the ramp. And the last one, we were able to measure the highest point is going to be 60 millimeters, and the distance is going to be 0.32 meters.
This is our timeline of the project. As you can see on the first part of the project, we had all the calculations and design and also assembly of the quadcopter. For the second part, we wanted to focus on the release mechanism and also the testing. So we already had all that by summer, and we can just focus on the testing. This is our cost. We have a total cost of $3,300. That's including the camera and the release mechanism. The cost without the camera was $2,400, which is substantially low. Without the camera that we chose, which is an FPV camera, first person view, because we wanted to do an inspection system. This is a cost that we did not have in mind from the beginning, but it was important for the purpose of the project, which is the testing. We have to take into account the malfunctioning parts and the crashes that it consequently had. The total cost for the crashes was $729. We also figured that we needed to test, take some time practicing flying the quadcopter because it's not easy. So we include the price of a mini quadcopter. The total cost without the camera went up to $3,200. So we have to take into account that the system for the video is not the same that we chose from the beginning. For a global perspective, this is a project that we can use globally. We have to create manuals and we have to provide the necessary training to fly it and to operate it. Next.
Let's answer our conclusion. While doing this project, we didn't take into account unexpected events. They were the crashings of the quadcopter. While testing it, it crashed twice because it's really hard to maneuver. Every time it crashed, we had to replace parts. That is what made us go overboard our budget and not able to include the SAT camera that we wanted to include in the project. And also the other thing was that every time we crash the quadcopter, the replacement parts, they come from other places of the world or other places in the United States. They take 2 or 3 weeks in order to get here. So that lead time will push our testing back. The third thing to have in mind is that the prototype is really hard to maneuver. Therefore, if this is going to be sold around the world, it will need to be provided some training for the persons that are going to maneuver it. And finally, we think this is a really good project. It was rewarding. We're using some innovation. We were proud of the engineering work that we did. Therefore, we think it is possible to sell it in a lot of markets. This is the first venue that we have for the testing.
So you can see we had a very windy day. That's why you see the quadcopter kind of trying to stabilize itself. We are trying to align it with the starting point so we can measure the distance it goes up and how far it travels.
Questions?
Okay. Dr. Tamonte.
Okay, the first question I want to throw at you, and it was in your objectives, was to include stability control sensors to better manipulate the vehicle. Why I asked the question, partially because you showed me that it was unstable in wind, but bigger concern to me is that when you have fire, you've got combustion. When you get combustion, you're sucking oxygen, air into it. It creates its own thermoclines. You end up with a situation where the stability of the air around the fire is not that great. And so how are you going to compensate for that?
It wasn't the constraints, even though I forgot to say it. Our main purpose is to use this in a high-rise building. So let's say the window is open, if they have flames coming out of it. The idea is that the quadcopter is below the frames. If it's on top of the flames, it will run the electronics. So it's below the flames, and it has a software called RDFlyer, which is controlling the stability of the quadcopter, and the electronics are not compromised because they're not exposed directly to the smoke.
That's when we chose the release mechanism to be on top of the quadcopter.
Which
Okay, now, I mean, will that fit through a window?
No, it's not going inside the window. It has
So how do you get to the majority of fires? You're going to basically take care of the
It's
fire
gonna go
window?
up, and that's why we decided to have strong springs, so it will launch the ball a good distance, so it will go inside the window, so we have a clearance from the propellers, from the quadcopter to the building.
Any other question, Dr.
That's my
Tamonte?
question.
That's it, Dr. Basil? Oh, he's not here.
He was, a second ago.
Oh, any other questions? Dr. Levy?
You're saying the software was the thing that you had that would take care of the PID aspect?
Yeah,
for
part of the
this
design, we have to take into account the stability. That's why we chose the best sensors that we found. Of course, we have to take into account the price, but those were the best sensors. We have the flight controls, and we have a RDFlyer, which takes care of almost everything. It also has a GPS sensor. The purpose of that would be to just give it like directions automatically, and it will go from one place to another. We didn't test that because we were having hard times trying to manipulate it. It's not hard
So
to.
how far do these springs shoot the ball?
0.7 meters.
0.7 meters?
0.7 meters.
0.7?
Oh, 0.7
No, no,
meters,
no.
0.7 centimeters.
7 centimeters from this,
Well, no,
from this
no, no,
point.
no.
That's about 2 feet.
Now, how far does the ball get shot by your spring?
How far? Until the highest point is going to be,
No, how far out?
how far
The
out?
thing is that we only measure to the first point it touched the ground because we don't know how long the ball is going to travel once it touches the ground on the building that's on fire. So
Well-
that distance to the first point is 7
But
centimeters.
let's talk, as they say, bottom line. Okay, you're going to put this thing at some point where it's going to fire the ball basically at the height of the window. Okay? So all you want to know is that distance from where your release is to where the window is.
Yes.
Now, if you're telling me that all this is doing is 2 feet, okay, then you're back to the problem that Dr. Tomato is talking about in the fact that you're right in the middle of where this updraft of air is happening. So, I mean, I could understand if you had, if you were off, let's say 10 feet and firing this thing into the window where that, you're away from where the smoke and the heat and everything else is coming out of the window. But if you're that close, you're going to be affected by the temperatures of
I
the
think
fire.
a good way to come up with a solution is to include culverts that can cover all the electronics in it so the quadcopter doesn't seem affected when it comes close to the fire.
Yeah, but
Yeah,
I'm not talking about the electronics. I'm
It's
talking about
stability.
the updraft on your propellers.
That was
itself is
gonna
have
pull
an
the system
effect.
into the window.
Absolutely.
Yeah, can I say something? Since the helicopter doesn't have the mass, when you try to throw something out of the helicopter, you are not going to have to that much distance. How strong you are going to put the spring, the helicopter is going to go back. So if you want to increase the distance, then you have to put a rocket inside that ball, and that ball, after it gets out, it has to fire and it has to go in its own propeller.
So it's a secondary thrust to the ball.
Right, but the other aspect too is that if you don't fire it with enough energy, how do you know that the ball is going to hit and explode and release the
That's
chemical?
why we have the camera. The camera has to be light fit, so you know exactly where the quadcopter is placed on the building.
Also, the ball is not supposed to explode. It's activated by heat. So as soon as it enters the room, 3 seconds after that, with the heat of the room, it's going to explode. We're not measuring the impact of the ball.
Ah, okay.
We just want to
Alright.
put it in the
Yes,
right
Did you-
position.
Did you say that someplace?
On the specifications of the.
It was in the video, but.
Yeah.
No, I'm saying, is that specification?
Yeah, that is the
way
specification
ball-
of
The wall,
Yeah.
yeah.
Yeah, right at the beginning.
It activates within 3 seconds.
Right there.
Okay, I think
Okay, unrelated question. It's basic Newton's third law. Once that spring launches a ball, there's going to be a reaction on the quadcopter. How is that taken into account for stability of the quadcopter?
We're using our flyer and so forth. And also we try to reduce the weight as much as we could by reducing the thickness of the launching ring.
During the testing, we thought about putting springs also here to work as a softening, how do you call that?
A damper?
Temper, yes. But it worked, but it wasn't making that much of a difference. The difference was made when we took it back and we let this go all the way up. That's why we put the stoppers up here, not up here. So it was launching the ball further than where we wanted to do. And also we we thought that we were going to lose stability when during flight, but it was very stable. The controllers were perfect, and
No, I'm not concerned about within flight, I'm concerned about when you launch that, the action and reaction effect on the stability of the quadcopter. That's what I'm talking about.
how do we take into account that?
Yes, so how do you, what response mechanism is built in to stabilize a quadcopter to compensate for Newton's third law?
Okay, the way that we calculated if it was going to work, we know that the weight of the total the total weight of the quadcopter is one thing, and the weight of the ball is something else. So we did the calculations with the inelastic collision first, to take into account how far it was going to travel by the velocity that the quadcopter would have at the end. So we saw that since this is put in a thrust of 12 kilograms at the maximum capacity, and the weight of this is going to be it's going to travel very little. It's going to be like 10 centimeters back. That's launching the ball, because it's compensating for the weight of the ball. This is very heavy. It's very heavy, but the weight of plus the battery is also putting some weight into the
The
quadcopter.
autopilot compensate that kick.
Yeah, the
from
way the
spin,
motors
from
have to
spin.
behave in order to balance again the control.
The autopilot take care of all that maneuvering.
Okay, well, that's something you may want to emphasize because it's a very important.
Okay.
And the autopilot has a 3-axis gyro, a barometer, a magnetometer, and a accelerometer. So all that works together to keep the quadcopter in place as long as you don't move it from the control. So when we were flying, if we just wanted to stay in one place, we would leave it there, and even if we would try to move it, it would stay there. That's also part of the GPS purpose.
Okay. All right. Any other questions?
At what temperature do the propellers burn?
At what temperature the propellers
Burn.
burn to compensate for how close it is to the.
What's the specification?
Well, we don't have calculations, but this is carbon fiber, so we'll have to test the temperature when burning the propellers. We didn't take that into account because we are not trying to get the quadcopter into the building just as close as possible.
I think what Dr. Levy is saying, at some point, the heat is going to impact all of those components. And if you lose one of those propellers or rotors, you've lost the stability of the quadcopter. So what built-in response mechanism you have in the systems operation to ensure that temperature effects on those rotors are not going to impact the overall performance? Am I interpreting your question correctly? Yeah.
We didn't take that into
Something to consider.
Yeah.
Yeah.
Another one is ambers.
Yeah.
How do you manage flying particulate that's burning? You know, because you've got open exposed electronics there. You take that helicopter down when you take an amber right on that board.
Our main focus was the release mechanism. It wasn't too much of the quadcopter itself. We weren't trying to put the best quadcopter, but we were focusing on the release mechanism because quadcopters are there everywhere. So this type of system is not anywhere. So we were trying to focus more on the release mechanism than on the frame itself. For that will be like a different project. We have to focus on what's going to be here, protecting the motors and electronics. But even if we wanted to choose something that protects all the electronics, this would be easier because they will have the plates that are easy to manipulate, cut, resize, and we have to take into account the antennas and the signal receivers and all that because they have to be exposed to the air. This was our main concern in the project.
Okay, well, thank you for that. We're over time on this one.